Welcome, everybody. Happy to introduce Brett Palm, who is originally from Sheboygan, Wisconsin. He did his undergraduate work at Dartmouth College in chemistry. He joined the Jimenez group at the University of Colorado working in analytical chemistry. He has been working with aerosol mass spectrometry and oxidation flow reactors, which are also known as PAM chambers, in a variety of different field locations. He worked with us at NCAR at the 2011 Beacon Rhombus campaign, where we met for the first time, and that's a ponderosa pine forest at the Manitou Experimental Forest here in Colorado. He's also had deployments in Go Amazon in Brazil during 2014. His research interests are in the impact of natural and anthropogenic activities on the composition of the atmosphere, particularly through the development of field measurement techniques. So we're welcome to Brett, and we'll look forward to hearing what you have to say.
Thanks, John. Thank you guys for inviting me to give a seminar today. This is a really great opportunity for me to practice my thesis defense. So I'm Brett Palm. I work with Jose Jimenez at CU. I'll be defending in 3.5 weeks now. So today I'm going to present my thesis work to you guys on the development and application of the oxidation flow reactor technique, studying secondary organic aerosol formation from ambient air. It's quite a mouthful. Hopefully that'll make sense by the end of the talk. So here you can see a picture of two OFRs on top of the container in Brazil, the Amazon forest in the distance. So I'd just like to start by thanking all the various funding agencies that helped with this project, particularly an EPA STAR Fellowship and a Series Graduate Fellowship as well. So I'll start by introducing what it is I'm studying, secondary organic aerosol formation. So I'll give a quick overview of how that happens in the atmosphere and what we know about it. And then I'll introduce this concept of the OFR. I'll give you an introduction to what the measurements look like. And then I'll discuss the advances that I and my colleagues have made in interpretation of these measurements and how we can use it as a technique to study SOA formation. And finally, I will show you the results of some field measurements oxidizing ambient air to study SOA formation from the ambient precursors in several different contrasting locations, starting with the pine forest at Beacon Rhombus, which is an NCAR site. Briefly touch on urban measurements oxidizing ambient air during the CalNex campaign. And then once we've done the two extremes of rural forest and urban areas, we'll discuss the Go Amazon campaign, which was obviously also biogenic, being in the Amazon forest, but it was downwind of the city of Manaus, which is a major metropolitan area. And so we expected to have mixed sources. And then I'll summarize what we've learned from these measurements at the end. So organic aerosol in the atmosphere has a number of different sources, depicted here in pretty colors. So you can have direct particle emissions of organic aerosols, such as forest fires, combustion sources. On a global scale, these typically represent a relatively small fraction of all the organic aerosol. And it's not the focus of my work. The focus of my work is the secondary processes. So you get gas phase emissions from biogenic sources, anthropogenic sources, forest fires, biomass burning. And these gases get oxidized in the atmosphere, typically by OH, ozone, and nitrate radicals, to form low vapor pressure gases, condensable gases. So these gases can condense to form new particles or condense onto pre-existing particles. So this is, if these gases are organic, we call a secondary organic aerosol. So there are other processes that form SOA in the atmosphere, but the process that I'm focusing on today is this gas phase oxidation pathway. So just another schematic to illustrate this process and to introduce some terminology that I'll be using. So this is a space where you can sort of define any organic molecule in the atmosphere. The y-axis isn't terribly important, it's oxidation state, but what's important for us is the vapor pressure, the volatility axis on the bottom. So more volatile emissions are on the right, less volatile is on the left, so gas phase, particle phase. So what we need to take away from this graph is when I talk about VOC emissions, these are gas phase emissions. On the more volatile end, they're relatively easy to measure and quantify. These gases can get oxidized, and when they get oxidized, you add oxygen to it, they become less volatile. typically, and they can form semi and intermediate volatility, or S and IVOC compounds. These gases, as well as the original VOCs, can be oxidized to form low volatility compounds, or LVOCs, that can condense to form particles. And so this is the process that we're trying to replicate in the oxidation flow reactor, is taking the original emissions and any gases we find in ambient air and oxidizing them to form particles. So this is the oxidation flow reactor that we use. OFR is sort of a general term. There's a number of different flow reactors out there, but the one we use is called the potential aerosol mass reactor, designed by Bill Brune at Penn State. And so you can see a few different configurations. We can run it with the inlet plate open, the smaller hole, or with the inlet plate all the way off. We get a lot of interesting visitors attracted to the UV lights inside the reactor, and a cool frog in the Amazon that I definitely didn't touch. So this is a schematic of how we operate in the field. So here with the OFR, as you saw, it's open on one end. We pull in ambient air into the reactor. Any gases or particles that are in ambient air get sampled in, and inside we introduce an oxidant. Now here I'm showing OH production using the UV lamps that you saw in the last slide. So the oxidant oxidizes anything that comes in, and we form these low volatility compounds that can condense, which they do, and then we sample them. We sample with a series of valves, so we can rapidly switch between measuring oxidized air and ambient unperturbed air, so we can tell the difference. We measure the particles using AMS and SMPS, typically gases with PTRMS, and use an ozone monitor as a proxy for the amount of oxidant we have from OH oxidation that I'll discuss shortly. So there's two different kind of experiments you can do with this. You can study SOA formation, as I just showed, and if you have enough oxidant, you can study heterogeneous oxidation of pre-existing aerosols that I'll discuss also soon. So this technique is really an alternative to large environmental smog chambers, where we have a short residence time, typically between 2 and 4 minutes. So this really cuts down on wall effects, particularly particle phase losses to the walls. It's also a portable technique, so we can take it into the field, set it on top of the trailer, and do essentially really short chamber studies in the field with ambient precursors. So I showed you an example of OH oxidation. We can also do ozone and nitrate oxidation by injecting ozone or N2O5, which thermally dissociates to give NO3 in a dark reactor. I'll show a little bit of those results later on. And you can also sample with any other instruments on the back end. It's a versatile technique. So now I'll give you an example of what these measurements actually look like. This is a picture in Brazil again. The two OFRs, we might have been doing OH oxidation in one and ozone in the other, side by side. This is the Amazon forest in the distance looking in the direction of Manaus. So the emissions would be coming at us. You can also see, if you look closely, there's a forest fire off in the distance. And so this gives you a quick idea of the various sources of SOA forming gases that might be coming by the site. So now to the measurements. This dark line is the ambient organic aerosol concentration. And now if I show the amount we measure after oxidizing the air by a constant amount, roughly 3 equivalent days of atmospheric aging, you can see that we're forming SOA in the reactor. And the amount that we form is variable even within a given night, and the yellow bars are daytime, but we typically see more SOA formed from ambient precursors at nighttime than daytime. So the hypothesis is there are gases in ambient air that are entering the reactor, and we're making aerosol out of them, right? So we can compare this to ambient measurements of VOCs. So copaine is a single sesquiterpene measured with gas chromatography. Monoterpenes is well measured on a faster time resolution in ambient air and after oxidation. So we can see they're being oxidized away. These spikes correlate really well with when we saw SOA formation. So this gives us a lot of confidence that what we're doing is making sense here. It doesn't always match up with monoterpenes, for instance. The end of the second night here, there were hardly any monoterpenes, no sesquiterpenes, and we were still making a small amount of aerosol. And so presumably, maybe that was a time when anthropogenic precursors were passing by the site or something like that. So that was an example of constant OH exposure. Typically how we operate is in about 2-hour cycles where we step through different oxidant concentrations. So the black bars represent UV lights are off, so no added oxidant, and then increasing amounts of OH exposure with the increasing color towards yellow, ranging from hours up to several weeks of equivalent photochemical age. So again, we show the ambient organic aerosol and sulfate aerosol and the amount after oxidation. This is the behavior that we see, is that we form increasing amounts of organic aerosol up to approximately a day of photochemical aging. And then at higher ages, we see a lack of new SOA formation and a heterogeneous loss of the pre-existing OA. This is behavior we see everywhere. And sulfate has a slightly different behavior. We only convert SO2, oxidized SO2 with OH to form sulfate aerosol at the higher exposures above about a week, because the rate constant with OH and SO2 is a lot slower than for biogenic gases. So we can take these 2-hour cycles and add them up for an entire campaign. This is from the Beacon Rhombus campaign. Now I'm showing the absolute SOA enhancement. So if it's greater than 0, we're forming SOA. If it's greater than 0, and losing SOA if it's less than 0, relative to the concurrent ambient measurements of OA. So what we see is that we form the maximum amount of OA, again, in this range around about a day of aging. And even within that range, we can see anywhere from no SOA formation to a lot. And so just as a side note, this indicates to us that we don't have substantial effects of off-gassing from the walls inside the reactor or something like that, producing large amounts of SOA. And then again, at higher ages above about 5 days, we see this loss of aerosol, which we interpret as being heterogeneous loss of the pre-existing OA. I'll discuss that concept a little more soon. So this is all times of day shown here. As I said before, we see more SOA being formed at nighttime than daytime. So we can take this graph, split it up into daytime and nighttime, and bin it. So here you can see nighttime and daytime. We see about 4 times more SOA being formed at night. This indicates that the concentration of SOA forming gases is higher at night, which makes sense because there's no photochemistry happening, so these precursors might be building up. So there's kind of 2 different kinds of experiments that we can do. If we want to study SOA formation, which is what I want to do, then you need to make sure you're in this range of OH exposures around about a day, where heterogeneous oxidation is minimal. And these molecules are being oxidized by OH 1 time or 2 times or 3 before, up to several times before they have a chance to bump into a particle and condense to form SOA. So we're not oxidizing them crazy amounts. Whereas at these higher ages, we are oxidizing them crazy amounts, 5 times, 10 times before they have a chance to find a particle. And so these molecules in the gas phase are fragmenting apart to give volatile products that no longer condense. So we no longer see that SOA formation, and then everything that we measure is a loss of the pre-existing OA. And then we just kind of ignore the intermediate range because it's a mix of these 2 effects. So hopefully you have an idea now of what these measurements look like and how we could use this technique. So now I'm going to step through this animation again and talk about several points where I've been focusing on my thesis work to try to interpret these measurements and understand exactly what's going on. So we have the gases and particles entering the reactor. We introduce an oxidant. The first question is, how much oxidant do we have? It's a non-trivial question when you're using UV lamps to produce OH. We don't have a way to measure the OH in situ. It would be very difficult. And so we'll discuss how we figure out how much OH we have or other oxidants. The next question is, if we're trying to study OH oxidation, how do we know that we're not doing photolysis or some other oxidative process? We need to make sure that we're saying it's from OH oxidation that it actually is. So we can oxidize these gases to produce condensable gases. But the condensation process is not instantaneous. So how do we know that we're quantitatively condensing and measuring these particles with AMS? They could, just as in a chamber, they could condense onto the walls of the OFR. Or if there's too much oxidant, we could be reacting them away. So they condense, and then the last question is how how can we compare this condensation, this SOA formation to chambers and to what happens in the atmosphere? How do we know that the LVOCs that we're making are representative of compounds that you get in a chamber study? So the way that we did that is by measuring SOA yields in the reactor under conditions of the reactor and comparing with chamber yields. So once we consider all those fine details of the analysis and the technique, the overall question that I'm trying to answer is, we have these measurements of gases in the atmosphere. We can estimate how much SOA should be formed by oxidation of these gases. And then we can compare that to the amount that we actually measure to be formed. And can we achieve closure between this measurement? Do we understand the system? So let's step through these questions. First one is, how much oxidant do we have? For OH oxidation, another member of Jose's group, Jie Peng of postdoc, has done extensive modeling of OH chemistry, of oxidant chemistry in the reactor. So I'm not going to get into great detail on his modeling. I can refer you to these papers. But a model output is, so the model, the OH exposure in the model depends on several things, including how much ozone, it's a measurable quantity that we can put into the model, how much ozone we get out of the reactor, ambient water vapor concentrations, and the VOC concentrations or external OH reactivity. So one of the model outputs is OH exposure, which we think we can estimate within about a factor of 2 or 3. And as you can see here, we convert it to equivalent age in the atmosphere by dividing by an average OH oxidant concentration in the atmosphere. So the range that we achieve for OH oxidation is from hours up to several weeks. Ozone oxidation is much simpler. We can simply measure the amount of ozone we have in the reactor that we're injecting and multiply by the residence time. So here, these graphs are a little small, but we have the OA enhancement from ozone oxidation. So the amount of SOA formed, binned into 2 groups for low concentrations of monoterpenes and higher concentrations. So the more monoterpenes we have, the more SOA we can make, which makes sense. And the range, the point of this is the range that we can achieve is from minutes even up to about 5 days of equivalent days of ozone aging. Nitrate is a similar thing. I put together a model to estimate the nitrate exposure, which I'm not going to discuss the details now, and you can find in these published papers. But nitrate as well, when we have more monoterpenes, you get more SOA formation over the range from hours up to several days of equivalent aging, assuming 1 ppt of nitrate, which is also a very variable quantity in the atmosphere. So a lot of the work that I've done, though, is verifying these model outputs. So the way that we verify them is by comparing measured VOC decay to the modeled VOC decay. So here we had CO that we injected into the reactor, and ambient toluene and monoterpenes being oxidized by OH. We can measure the fraction remaining after oxidation and compare it to the amount that should remain according to the modeled age. And we get within about a factor of 3 on this. So we feel fairly confident that we know we're in the right ballpark of oxidizing the precursors. Ozone oxidation, you can do the same comparison. It's the fraction remaining after oxidation as a function of age. So the more age you get, the less fraction remaining, and it matches fairly well. You can also see it in a time series of ambient monoterpenes in black, and then green is measured after ozone oxidation, where we were stepping through a range of ozone concentrations, and the modeled ozone remaining matches very well. Same thing with nitrate oxidation. You can see in the time series best that we can match the model and measured remaining in the OFR. So we've done a lot of work trying to figure out how much oxidant, making sure we know how much oxidant we had in the reactor. Another question is, in particular for OH oxidation, how do we know that we're doing OH oxidation and not some other process? Again, this is a lot of Jie Peng's work that I'm not going to go into in great detail other than to give you an overview of the results. Typically under our field conditions when we're oxidizing ambient air, if we're trying to study OH oxidation with UV lamps, that's the dominant pathway is OH oxidation. He found that you can get into trouble if you are under specific conditions. You can have these other pathways be important, in particular, very low relative humidity. So if you're doing a laboratory study using dry air from a tank, you can, the other processes become important. or if you have high external OH reactivity, so high VOC concentrations. For instance, if you're injecting ppm levels of monoterpenes, you're just converting all of the OH to HO2 and suppressing the OH, and then the other processes become relatively more important. But we don't have those conditions under our field studies, and so we were in good shape. All right, so the next question is, we have these gases, we know we're oxidant, we know we're doing OH oxidation. We make these LVOCs. What happens in the reactor? What we want to happen is we want them to condense onto particles. This is going to be the dominant fate in the atmosphere. But in the reactor, we can have these other fates. It can condense onto the OFR walls, just like in a chamber study. It can continue to react with OH, and if it does so enough, it can fragment apart and no longer condense. And it could simply just exit the reactor without doing any of these, where it'll quickly condense on the sampling line walls. So as part of my research, I put together some modeling. I don't expect you to read all these tiny equations other than to know that the condensational sink of the aerosol is one of the controlling factors in determining how much will condense onto the particles in our limited residence time. And so the output of this model is the fractional fate that will follow each of these pathways. And so you can see that here for a typical example where we had a total of about 5 micrograms per cubic meter of aerosol in the reactor when we were forming the most aerosol at around the 1 day range. And so you can see that as we form aerosol, the condensational sink increases and the fraction that condenses on the particles increases up to a maximum of about 70%. And so we can correct for the other 30% to relate these results to what would happen in the atmosphere. And so this is the range of highest SOA formation. If we had about 1 microgram per cubic meter of aerosol, you might have 30% or 20% of the gases condensed, and then you have a very large correction. So you want to try to avoid those conditions. If you have 10 or 20 micrograms, then you get 95% of it condensing, and life is good. So this really illustrates that at the high exposures, this blue becomes very important. So this is a parameterization for the molecules that will react 5 or more times with OH before finding a surface to condense on, a particle to condense on. And so this really illustrates that we're oxidizing these molecules many more times than they would be in the atmosphere, and destroying everything in the gas phase. And then what we measure is the result of heterogeneous oxidation. So one question is, how do we know this model makes any sense? Well, it would be difficult to inject LVOCs in the gas phase and measure their fate. So what we did is, using field data, we verified this by looking at sulfuric acid formation. Sulfuric acid is a very low volatility molecule, the result of SO2 oxidation. And so if we compare the measured amount of aerosol sulfate enhancement compared to the amount predicted in the relatively few plumes of SO2 that came by the beacon site, we're not measuring as much as we should. And so if we apply this correction, it's a bit noisy, but it follows the one-to-one line much better. And this gives us a lot of confidence that this is indeed a process we need to pay attention to in the OFR. And that it should also apply to organic gases. So these LVOCs that are condensing, how do we know that the ones we're making in the reactor are sort of representative or similar to what you get in a chamber study? So to do that, we measure the SOA yields, where we injected a known concentration of several VOCs into ambient air at the start of the reactor on top of a trailer in Brazil. And so we can measure the SOA yields under the conditions that we're running the experiment, ambient conditions, real seed aerosol, et cetera, and apply all these corrections and avoid non-OH reactions, and then measure the SOA formed and the VOCs reacted. So this is the space that we're going to fill up. SOA yields from 1% to 100% as a function of the organic aerosol concentration. This green line is a parameterization for terpenes from chamber studies given in Simpidi 2010. And so if we put our calculated SOA yields on here for different species and OH and ozone oxidation, they follow the line very well. There's some variability within species and from oxidants, different oxidants, but there's also going to be variability in the atmosphere between species. This green line is just a parameterization that has its own uncertainties. So this looks like pretty good agreement to me. We can compare sesquiterpenes with our measured sesquiterpene yields. also looks very good. Oops. Toluene as well, certainly within our ability to determine. And here's isoprene, and here I'm showing two different chamber parameterizations, so you can kind of see the variability even in chamber parameterizations for these SOA yields. And so if I wanted to be very precise in my quantification of SOA yields, I would do this in the laboratory and not in rainstorms in Brazil. But the conclusion that we get from this is that these SOA yields in the OFR are reasonable, and they're not that different from, not substantially different from chambers. And so we have confidence that when we bring in VOCs and we're measuring them in ambient air and we oxidize them, we should get the proper amount of aerosol coming out the other side. That's great. So now we've gone through all the fine details of the technique. And so now we can kind of compare the measured and predicted SOA formation in the reactor. We've taken measurements in field in many different locations. I'm going to focus mostly on beacon rhombus, briefly touch on CalMax, which was Pasadena urban air, and then skip to Go Amazon campaign 2014. We also went to SOAS and flew it on the airplane a few times, but that wasn't part of my thesis work. So beacon rhombus, here's the OFR on top of the trailer during setup, hopefully. It's quite dirty down here. We were right in the canopy. Here's another picture of it. There's not a whole lot there except pine trees. This is the Manitou Experimental Forest Observatory site. And this air is typically dominated by clean continental air from the west coming over the mountains, occasional air influenced from the Front Range, but for the most part, we expect it to be a biogenic dominated site. Indeed, skip right to the results. The maximum SOA formation, so in that range around 1 day of OH oxidation compared to ambient monoterpenes, and it correlates very well. And biogenic things correlate with biogenic things, monoterpenes and sesquiterpenes. And so we really think that this is a site where the SOA formation potential is dominated by biogenic things. So we can do this measured versus predicted analysis, where the predicted amount is these chamber parameterization SOA yields as a function of times the VOC that's measured or predicted to react in the OFR at those ages. This is for nitrate and ozone oxidation, measured amount versus predicted amount, and they match rather well. The predicted amount is definitely consistent with the amount that we measure just from terpenes, from monoterpenes and sesquiterpenes. So the molecules with double bonds in them, carbon-carbon double bonds. So this looks great. The concept seems to be working. However, if we look at OH oxidation, now we're forming about 4 times more SOA in the reactor than we predict from these terpenes and a handful of other molecules like toluene and isoprene that were measured in ambient air. So the question is, what are the other gases that are in ambient air that are forming this SOA by OH oxidation, not by ozone or nitrate? So during the Beacon campaign, there were a lot of different measurements there, and there was this attempt from Jesse Kroll's group to quantify the entire carbon budget in the atmosphere, both particles and gases. And so when we're oxidizing air in the OFR, this is what we're oxidizing. And so the SOA has to come somewhere from in here. So I'm going to add another column called potential OA. So this is, we'll carry over the ambient OA, and this is the amount we form on top of it from oxidation. So where are we going to get this potential SOA from? Well, we're just carrying this over. We're not forming OA. It's already OA. None of these molecules, acetaldehyde, et cetera, formaldehyde, are not. These are not going to form SOA. Also, in this column, these are long lifetime VOCs, so less reactive VOCs, are not reacting with ozone or nitrate to form SOA. We can account for all the terpenes that are in this column, and that gives us closure on our measured versus predicted, and we don't require any yield from these S and I VOCs, which is fine. But OH is a different story. Again, the potential OA, where is it going to come from? Not from ambient OA, that just gets carried over. These gases are not making aerosol. We can account for all these, benzene, toluene, terpenes, and that gives us a quarter of what we need. So what that says is that these S and I VOCs, which are, there's some speciation of these, but typically they're difficult to speciate and quantify. And so Jesse Kroll's group had a novel instrument to try to quantify the bulk amount of S and I VOCs. And so we think that those have to be the other source of SOA in the reactor. So we can add a yield from these gases. So this is again measured versus predicted just from VOCs. 4 times more aerosol is formed, so ambient VOCs alone can't explain it. So we're looking at the S and I VOCs. So we can apply an SOA yield to them, assume that they are the rest of the source, so we can figure out what yield we need to reach the 1-to-1 line. And we do that, and we require between 18 and 58% within the relatively large measurement uncertainties. To achieve closure, we maintain a high correlation with the limited time series of measurements. And so this gives us confidence that these are the gases that are in ambient air, forming aerosol. So what are these gases? Where are they coming from? The story kind of explains itself, but we've seen this already. The maximum SOA formation in the reactor correlates with monoterpenes. The total S and I VOC measurement correlates with monoterpenes and with sesquiterpenes. And so this is, everything here is biogenic, is what this story is telling us. They are likely oxidation products of the VOCs, or they could be co-emitted direct emissions of S and I VOCs. We can't say anything about that, but they're very likely biogenic in origin. So just to give an overview now of this simple forest system, single source biogenic source system, we have terpenes being emitted upwind of the OFR. As they travel downwind, they're being oxidized in the atmosphere by a different oxidant for a different time of day, forming aerosol and forming these oxidation products. They may also be directly emitted into that same air. Now as it's approaching the OFR, we have more terpene emissions from the trees nearby. And so this is the soup that we're oxidizing in the OFR. When we do that, we can form aerosol from the terpenes. We can form aerosol from all 3 oxidants. But from the oxidation products, the SiVOCs, we can form only from OH. So does that make sense? We can look at candidate molecules here. Alpha-pinene reacts relatively quickly with each of the 3 oxidants. But once you do that, you react away the carbon-carbon double bond. A typical oxidation product would be pinenaldehyde, which now reacts very slowly with ozone and nitrate radical. And so we're only going to be able to make aerosol on these timescales from OH oxidation. So this story seems to be consistent, all biogenic source. The concentrations in here and the relative concentrations of terpenes and S and I VOCs depend on light and temperature dependent emissions, there's boundary layer dynamics, different deposition rates, different oxidant concentrations. So we might expect diurnal changes in the SOA formation potential that we find in the atmosphere. And indeed we do. So in green you can see this is the measured SOA formed in the reactor. Changes a lot with time of day. This is noon. The blue is the amount predicted from VOCs. And so the difference between the two would be the contribution from the S and I VOCs. So what do we learn from this forest system? Well, this process of SOA formation is not instantaneous. When you have VOCs being oxidized, they go through this intermediate, or they can go through this intermediate S and I VOC phase. And understanding what happens to those in the atmosphere is critical to be able to figure out how much SOA is eventually going to form downwind. So if they deposit, then they're no longer part of the process. And this also illustrates that the OFR is essentially a detector of SOA forming gases. It's a way to quantify S and I VOCs in the atmosphere by turning them into something that we can measure much more easily, which would be aerosols. So that's the biogenic picture, nice and tidy. Let's look at now a non-biogenic place, Pasadena. There are a few trees in the background, but it's a parking lot in a city. So we expect it to be dominated by anthropogenic pollution. I was not at these sites, but did a little analysis with it. So this is, again, the SOA produced by OH oxidation correlates well with trimethylbenzene, which is a anthropogenic emission, anthropogenic tracer. However, the amount of trimethylbenzene is very small compared to the amount of SOA we're forming, so there must be other gases. We can do the measured versus predicted analysis with all the available speciated and quantified gases, and we find that often we make more aerosol than predicted. So these unquantified, unspeciated S and I VOCs are likely important. we can look at this correlation between different molecules, which are probably hard to read, but the correlation between the SOA produced and the VOCs as a function of the reactivity towards OH of those VOCs. So the fast-reacting biogenic precursors have low correlations, but the fast-reacting anthropogenic precursors have high correlations. And so this suggests that the gases that are contributing to this SOA formation are likely anthropogenic. So this is just in contrast to the biogenic atmosphere, and everything looks nice. So now what about the Amazon field campaign? This was in Manaus, in the middle of the Amazon. This is the city of Manaus. It's a city of 2 million people surrounded by forest for 1,000 kilometers in each direction. We took measurements at both the T2 site and T3 site downwind. So this is the wind direction, came from right to left across the screen. So if the wind came from the city of Manaus, we might expect to see anthropogenic pollution maybe on top of whatever biogenic emissions were in the air. And if it came from anywhere else, we might not see anthropogenic influence. We sampled during wet season for 2 months, which we called IOP1, intensive operating period, and the dry season, IOP2. So we expected this mix of biogenic and anthropogenic, and also we expected enhanced biomass burning during the dry season, which you can see in these satellite-detected fires during the wet season and dry season when we were measuring upwind of the site. The site is the red dot, so there were a lot more fires, regional fires, during the dry season. So let's look at this, again, measured versus predicted SOA formation using ambient VOCs. The one-to-one line is down here. Again, same old story. We make a lot more aerosol than we can predict from just the VOCs. It's colored by time of day. So during the daytime, we might see less of a discrepancy. At nighttime, it increases. So yeah, again, these unmeasured gases, we're going on and assuming now that these are still SNI VOCs. We didn't have measurements of the total amount of SNI VOCs during these campaigns. The Beacon campaign was unique in that aspect, but people do a pretty good job of measuring VOCs, and so we're pretty sure that these are unquantified SNI VOCs. So the goal of what I want to do with this analysis is, what are the sources of these SNI VOCs? How much does each source, anthropogenic, biogenic, and biomass burning, contribute to this measured SOA formation? So how much influence does the city have, essentially? So we can start by looking at correlations with tracers for each of these sources. Here are the tracers shown for the dry season. For example, the SOA formation as correlated with monoterpenes, sesquiterpenes, isoprene are the biogenic tracers. Biomass burning is the sum of 4 individual compounds measured by GC, SV tag. NOI as a proxy for anthropogenic influence, and xylene's thrown in there as well. The correlations are all pretty low, and so this is consistent with having multiple different sources arriving at the site at different times. And so we don't have any information here about the quantity of how much of each source arrived at the site on average. So we don't have any measurements of SNI VOCs. We're trying to say something about gases that we're not measuring and that are very difficult to measure and typically not measured field campaigns. So what do? We have to get creative. As we saw during the Beacon campaign, when we did have a measurement of SNI VOCs, they were biogenic in source and they correlated with a biogenic tracer. And so we can go ahead and assume that for the purposes of this analysis, all of the SOA forming gases related to a given source, including IVOCs and VOCs, are going to be correlated with the tracer for that source. So then we can do a multilinear regression of the measured SOA formation against several of these sources, the source tracers, and we allow this model to fit SOA coefficients, I'm calling them. So the coefficient accounts for all the SOA that would form from this tracer and all the SNI VOCs corresponding to that, the source of that tracer. And then in the end, we can take the coefficient times the tracer concentration. So if I use monoterpenes and we pull out a coefficient, we multiply the monoterpene concentration by the coefficient to get the total amount of SOA formed from biogenic sources. So this is a hypothesis. Let's see how well it works. Let's look at the dry season to correspond with the correlation plots I was just showing. The tracers that I used for biogenic monoterpene, sesquiterpene, and isoprene. I allow them to be fit separately and then sum them together to form the biogenic source. For anthropogenic sources, I'm using NOI after subtracting a background concentration from biogenic sources. So the NOI showed a lot of variability above background, which was due to anthropogenic influence. And then for biomass burning, I have these 4 tracer molecules from Alan Goldstein's group. So we do multilinear regression, allowed to find the best correlation. Indeed, we do increase the correlation. It's not perfect, but it's looking better, so I think we're on the right track. Another way we can look at it is by looking at the contribution from each of these sources now. So here we have the measured amount of SOA formed in the reactor, diurnal cycle. And now we can add in the contribution from each of these sources as fit by this model. So the anthropogenic source, biogenic source, and biomass burning. This is for the dry season, IOP2. We can sum those sources up. And we match the measured diurnal profile fairly well. So before we try to interpret that, let's look at the results for the wet season. Same tracers, correlation is even a bit better. This is the measured SOA formed in the OFR. This is the model fit to anthropogenic sources, biogenic, biomass burning. And we can sum them together. It doesn't quite match as well, but the correlation's higher. So anyway, in this type of analysis, there's several things we need to consider. One is that you have to make sure that these tracers are emitted by just a single source. So if I want to call NOI a source from anthropogenic, I need to make sure that the variability in this NOI trace is due to anthropogenic influence and not, for instance, biomass. If biomass burning contributed a lot to the NOI budget, then we wouldn't be able to separate. Another thing in this analysis is that I'm allowing one coefficient to be fit for all times of day. And so that's assuming that the amount of SOA that could be formed, for instance, from anthropogenic sources arriving at the site, always has the same ratio to the NOI concentration at all times of day, which probably is not true. During the day, you might have a lot more photochemistry, decreasing the concentration of all these other unmeasured compounds, while NOI is sort of conserved concentration. And so these, it's likely to be imperfect because of that. One way we could address that would be to do this regression on specific times of day, so maybe separate out daytime and nighttime. I'm not showing any of those results yet. They're not ready for prime time. But in the end, so one of the things you need is that the tracer compounds don't correlate with each other. Otherwise, the model will not be able to separate them out properly. So if you start to decrease the time bins, then you start to get higher correlations between individual tracers, and it falls apart. So yeah, so these are the results that we have from this model so far. So what we can do is for each season, take the average contribution from each source, make a pie chart. So this is the wet season and the dry season. The total concentration of aerosol on average that was formed. So we saw more formation during the dry season. I'll first note that biomass burning source during the wet season is estimated to be small from this model, and then much larger in the dry season. And then the anthropogenic influence is about twice as large, estimated during the wet season and the dry season. And I'll discuss that in a minute, but overall, does this make sense? Well, we can look at the concentration of these tracer gases and how or if they change during the seasons. So the wet season are the blue bars, dry season are the red bars. So monoterpenes, sesquiterpenes, isoprene, NOI, they're not really changing between seasons. So we might not, from this graph, we might not expect the contributions from biogenic and anthropogenic to be so different between the two seasons. Biomass burning, on the other hand, the tracer concentrations were much larger during the dry season, and so we feel fairly confident that there should be much larger influence from biomass burning SOA forming gases at the site. The last two bars are the potential SOA, where the black is the sum now of biogenic and anthropogenic, and the brown is biomass burning. And so most of the difference between the two seasons can be accounted for by this increase in biomass burning, which gives us some confidence that it's doing something right at least. So some conclusions about this analysis. these are pie charts of the contribution of SOA-forming gases to the SOA potential in the OFR. These are not sources of organic aerosol measured at the T3 site. You could do PMF or other analyses to figure that out. But what we're looking at is contribution of these gases, the composition of these SOA-forming gases in the atmosphere at this particular site. So yeah, we're measuring those weighted by SOA potential, essentially. It's likely that biogenic gases are the largest source at this site. It would make sense. We're in the Amazon forest. There's definitely substantial anthropogenic influence at this site, possibly larger during the wet season. So one hypothesis would be if it's raining more often, it's cloudier, you have less photochemistry, and so the SOA-forming precursors can survive the transport several hours downwind to the T3 site, whereas in the dry season, if the sun's out, they might all react and form SOA on the way to the T3 site, so then they enter the reactor as OA and fall off of our radar. So it's kind of a complicated picture and a new way to look at measurements of SOA formation in the atmosphere. So we have higher confidence that biomass burning is more important, a little bit lower confidence at the moment between the biogenic and anthropogenic split. But that's definitely something we're looking into, and we're looking for more source-specific tracer gases that can really tell us for sure if there's anthropogenic influence or biogenic or biomass burning. So just to summarize everything I've shown so far, measured versus predicted analysis has been kind of the cornerstone of my thesis. At Beacon campaign, the wet season, the dry season, we've always seen more SOA being formed than we can predict. Calnex, and here's SOAS for good measure. So everywhere we go, these S and IVCs seem to be important. So what have we learned? These are all OH oxidation experiments. We almost always form more SOA than we can predict. These S and IVCs are important. And to really understand this process of SOA formation in the atmosphere, we have to improve our methods of measuring these intermediate gases, these sticky gases. So to conclude, I showed a number of improvements we've made in this technique, in interpreting the technique to study SOA formation. And so once you take all these things into account, these OFRs can be very useful tools to study either SOA formation or heterogeneous oxidation. The S and IVOCs are important in every atmosphere we've gone to. The simple conclusion is that when you're in a forest, you form SOA from biogenic things. When you're in a city, from anthropogenic, and Manaus is a complicated story that we're trying to investigate by any means possible. And so these OFR measurements really provide a snapshot of this process. So we take a slice in time where you have some gases that are just emitted, some that are halfway to being particles, some that are already particles, and elucidate it a bit and help us understand what the further challenges are in figuring out this process. And so with that, I will say thank you and take any questions.
We're going to use the microphone.
So it's very nice work. You're assuming complete conversion. Is there something to be gained by having a movable injector and measuring the time dependence in your flow reactor as you do with a typical OH decay reactor?
Yeah. So so you're talking about when I'm doing the predicted amount.
Yeah.
I'm for the predicting from VOCs. We use the OH exposure to calculate what fraction of the ambient measurement would be decayed and use that amount for the prediction. So for instance, toluene at those exposures of about a day, only half of it's reacted, and so we only add that much to the predicted amount.
And in terms of other gases, have you thought about acetylene and glyoxal in terms of producing SOA?
That's a good question, and that also goes along with the IEPOX SOA formation from isoprene. Since we have a very short residence time in the reactor, the processes that require reactive uptake don't happen fast enough in the reactor. Particularly, for instance, IEPOX SOA, Wei Wei Hu, a postdoc, has done a lot of work on that. We don't have enough sulfate the sulfate concentrations and the uptake don't scale with OH concentration. So we can make the IEPOX SOA, but it doesn't get taken up fast enough. So I would imagine for these like glyoxal and other things that might require uptake into liquid water content or pathways like that, probably also aren't being captured by this. So this is particular to this gas phase oxidation process.
Yeah, thanks. Yeah, you kind of answered this a little bit, I guess, but I was wondering how much of the ambient NOx gets chewed up since the SOA yields are dependent on NOx, how much that regime changes during the flow?
Yeah, that's a good question. So all the chamber parameterizations that I showed were low NOx yields. There's been some of that modeling work. Essentially, the NOx gets converted to nitric acid right away at the ages that we're considering. So we consider it all to be low NO chemistry that's happening. There's been some work. Jiapeng is about to submit, I think, a paper looking at trying to do high NO chemistry. So, for instance, one of the techniques they're looking at is injecting N2O, and that gets oxidized more slowly, to provide a source of NO through the reactor. So there are some attempts now of doing high NO chemistry with OH oxidation, but everything we do is low NOx essentially. Yeah.
Thank you. So in the picture of the two reactors in the Amazon, I saw some cows. Did they not have any influence at all?
There was no noticeable influence from the cows. They were not always there. The pastures were mostly empty while we were there. I was also operating a Picaro instrument, cavity ring down, and so we definitely saw the methane going up when the cows were there. But there's no noticeable correlation between the methane and when we formed SOA.
Yeah, no amines or anything.
No.
And the other question is, in your block diagram towards the end of section 3,
Which one?
Where you showed lots of SOA being formed at intermediate OH exposures and then not so much at longer OH exposures. If I understood you correctly, that's not intended to be a life history of a particular air parcel. Yeah, not that one. The
Further up.
The proportional one. The block diagram with 100% and the forwards.
Before this? Okay.
Forwards.
Before this or
Later
after this?
in the talk.
Later in the talk? Okay.
Yeah.
Sorry, I'm not sure which one.
This one.
Okay.
Yes. So this is showing the different fates as a function of different light intensities within the OFR rather than an evolution of any particular air parcel, right?
Correct.
Because of the changing ratio between OH and seed aerosol.
So this, if this kind of looks like the OFR, right? But it's not looking at the residence time. So are you saying like when precursors enter, they get oxidized, they start to form particles, and so the condensational sink is changing through the reactor?
I think the continuous nature of this plot is slightly misleading.
Yeah. Okay. Yes, I can explain that. I think so. Every experiment, every measurement that we take, we set the OH exposure constant, allow it to sit there and equilibrate for 15 minutes, and then measure for a couple minutes. And so one measurement is one exposure. So if you do a measurement at this exposure, these are the fates. If you then turn the lights higher, you do another measurement that's this exposure, these are the fates. And so you're not, we're not following the same parcel of air through exposures throughout the residence time. The one residence time or one condition is one measurement here.
I think maybe that could be made a little clearer in this plot.
Yeah. Thanks.
Thank you.
Hey, Brett. Can you explain again why the wall loss is not important? Is it important? Or
Why what's not important?
the wall loss?
The wall loss?
Yeah.
The particle phase wall losses are less important because the residence time in the reactor is a lot shorter. So in a chamber, you might have particles going to the walls on timescales of hours, and it prevents you from going over like a day. But in this reactor, it's 2 to 4 minute residence time, and so just the diffusional losses to the walls are a few percent. And we can check that by measuring through ambient air and through the reactor with no oxidant, and the OFR is always a couple percent lower than the ambient measurement, so we can correct for that. We do. But the gas phase wall losses, so the LVOC losses to the walls are more substantial because of the high surface area to volume ratio.
I had one more question, and it's similar to this plot where you're showing that there was sort of an optimal amount of organic aerosol that you were forming at around 1 day of OH exposure. And you might have mentioned this in your talk, but I didn't catch it. The AMS is limited to PM1, right? There's a cutoff. And
yeah.
So I'm just wondering, what does you're measuring particle size distributions. Is there any sort of bias that you're introducing by cutting off small particles as you increase exposure and maybe missing some mass? Does that make sense?
Yeah, that's a good question. The answer to that is in the supplemental section of this paper. We had to do a lot of, we did comparison between the AMS and the SMPS, essentially. So the SMPS can quantify the smaller particles, the volume of them, much better than the AMS lens transmission cuts off somewhere around 50 to 90 nanometers in that range. And so I did some sensitivity to find the cutoff that gives us the best correlation and a one-to-one slope between AMS and SMPS measurements, and corrected the AMS to include that mass, because when we're doing this experiment, we often, a lot of the mass that's formed nucleates into new particles. And so we do it, roughly half of it will condense onto the pre-existing particles and half will condense onto nucleating particles. And so we need to make sure we account for that mass as well in the mass produced. So I guess the answer is the AMS need to be corrected maybe 10% at most of the mass would be too small to be measured in AMS.
And anything on the upper end of the SMPS?
On the upper end, we didn't, the answer is no. We didn't need to correct it to achieve agreement. The larger particles don't grow that much with this mass, the mass that we're adding. But yeah, most of the mass would be added on the smaller particles, and if we're adding, say, 10 micrograms or a lot of organic aerosol, just those smaller particles will grow, and that's where the condensational sink will be, and so that's where everything will start to condense.
So are there any nonlinear processes that result from the fact that you are essentially skewing the relationship between oxidized gas phase compounds and aerosols compared to the real world?
Mm-hmm. Yeah, that's a good question. I'm not the expert on that, investigating that. The postdoc, Jip Peng, would be, and he's investigated it thoroughly. And essentially, yes, you run into problems at the highest exposures. For instance, with these LVOCs, we're not scaling the time they need to condense with how rapidly we're oxidizing them. And so that's one process that doesn't scale with OH exposure. But in terms of the oxidant chemistry, essentially HO2 and OH go up together, and the oxidant chemistry kind of scales fast enough. And we just don't capture any processes like reactive uptake that don't scale with oxidant. Does that answer your question? It's Yeah, so
I mean, you are creating an awful lot of oxidants because you have so much of H, right? So the ratio of oxidant to aerosol will be larger in the chamber than it will ever be in the real.
so at these exposures, the concentration, this is actually a good point. At these low exposures, the concentration of OH in the reactor is on the order of 10 to the 8, several 10 to the 8, which is similar to some chamber studies and maybe one order of magnitude larger than you could find in a city on a hot afternoon or something. So we're not too far removed in this area where we're making a lot of SOA. And one of the purposes of doing all those analyses of the process, investigating SOA yields and everything, was to be more confident that the results will actually apply to the atmosphere. So once you get up to here, then yes, we have oxygen concentrations that are far higher than you would get in any chamber studies or the atmosphere. So we haven't, our group, I guess, hasn't really made use of any of the data out here. It hasn't been the focus of these studies, but yeah, it's, yeah, even the oxygen concentrations down here are not as crazy as you might think originally. Jose has given some talks where he puts up a chart of preconceptions about OFR and the processes, and then how we've tried to investigate it and interpret, when things aren't as bad as they seem or when things are worse than they seem. But the general conclusion is that these processes are making sense with what we think should happen.
Okay, if there's no more questions, let's thank Brett again. And,